Okay, let's start. It's day 2, 17:15, and the next talk is about just-in-time compilers breaking a virtual machine. These two guys took CACAO, built some code generators for it, spotted that there are vulnerabilities and fixed them. And the talk is about their findings. Have fun and welcome Roland Lezuo and Peter Molnar.
Hello, I'd like to welcome you to this lecture about just-in-time compilers and how to break a VM by attacking its just-in-time compiler. Who we are, we already introduced. My name is Roland Lezuo and this is my friend Peter Molnar. And we both developed code generators for the CACAO virtual machine. And during development we saw, oh, you can do many things wrong in a just-in-time compiler. And said, yeah, let's look at this and make a lecture for the CCC out of this. In this lecture we will give you a short introduction to CACAO, what is it, and then switch to an introduction in just-in-time compiler and tell about some interesting implementation details. And then come to the main important point of this talk, security in just-in-time compilers, where can go things wrong, where to exploit stuff, where to look for. And we then did a code review of the CACAO virtual machine and we'll tell you what we found there and show you some exploits. Okay, CACAO is a Java virtual machine and I think you all know this, but it executes Java bytecode. The Java language is compiled into bytecode by the Java C compiler, which is machine independent. And on the host system or on the desktop computer or wherever a Java program is run, just-in-time compiler or interpreter, but in our case just-in-time compiler, comes in place and translates the bytecode into machine code, which then gets executed. CACAO is free software, it's GPL licensed, and it's available for 10 hardware architectures and 4 operating systems. Not each hardware architecture has each operating system, but so it's a highly portable Java virtual machine. CACAO uses a just-in-time compiler for performance and we're quite fast. And we use only just-in-time compiler, so there's no interpreter, so everything is compiled. What is a just-in-time compiler? Just-in-time compiler, the counterpart of a just-in-time compiler is a ahead-of-time compiler. This is what we all know when developing at home, compiling a program into machine code for one hardware architecture and one operating system. And the binary can then be executed on computers of exactly this type. And for just-in-time compilers, the idea came, why not use a higher representation, the bytecode, and compile it to machine code directly on the PC. So the developer can ship just one binary, which can be executed on many different architectures. Another observation was that many code inside a binary will not be executed at all. Just think of error handling cases. When the error does not occur, the code is never executed. And this is something a just-in-time compiler tries to use, and the method or code piece is compiled directly before it's used for the very first time. So when the method is executed or about to be executed, the compiler kicks in, generates the machine code and executes this. In the program there are always some methods which are executed very frequently. These are so-called hot methods and they are normally compiled with an optimizing compiler which takes more time. And thing is, code has to be generated quickly, that the execution time of a method is not too high. As you can imagine, there are some interesting implementation techniques necessary to implement a just-in-time compiler. One thing which is rather interesting, when the compiler kicks in. Look at the diagram and assume method A is already compiled. This method A will then call or invoke a method B. And there happens a normal Java method invocation which says basically branch to some address where this method is. But at this address there is no method, there's a compiler stub. The compiler stub has been generated when the class was loaded. For each method, the compiler stub is generated then. And the compiler job invokes the just-in-time compiler which takes the bytecode of the method to be executed, compiles it, places it somewhere into memory. The entry address of the method is different from the one in a compiler stub. And one job the compiler stub does is to replace these method entries in method A, which already invoked the compiler stub, with the newly generated address of the method P entry point. So we have runtime code modification. We modify the code during runtime, which means write, or execute cannot be implemented when using a just-in-time compiler, because just-in-time compilers in normal cases modify their code. The compiler stub further manipulates the stack so that its call frame is removed from the stack and then executes method P, which returns normally, and because the compiler stub has been removed from stack, we're back to method A. So it's completely transparent for method A. It does not notice there was a compile process during execution of method B. If there are any questions, you can always ask. When generating code, it always comes down to ORing together bit fields. That will be important later when we talk about the exploits, because we almost always have some integer overflows. Here you can see a rotate left double word then clear right instruction of the PowerPC 64. This instruction is said to be Turing complete, and it could be true. In the first line you see an assembler memo of these instructions and the arguments. And the color corresponds to the bit field inside the fixed 32-bit instructions encoding used on PowerPC 64. And this line here is a C macro used to generate the bit field from the arguments of the instruction. It was quite hard to get this one right, because there are many subtle details for this instruction. Another very important aspect for just-in-time compilers is that the information needed to compile the code is not always available when compiling the code. Sounds crazy, but Java demands lazy class loading. It's a kind of optimization. So if you have a method and you invoke a static method of a class, and the class has not been loaded yet, the entry point of the method is unknown. And in Java, you cannot load the class when such a method is compiled, but you can only load the class when the invocation of the static method is about to happen. This could be if the invocation is in an if branch and the branch is not taken, the method will never be invoked, so the class will never get loaded. This is rather hard part, and in CACAO we use something called patchers. When we generate the code, and you can see invocations of a static method on the upper left side, we load an address from somewhere and then branch to this address. That's the call register R10. And from somewhere we loaded the address. In case we did not know the address yet, because the class has not been loaded yet, we need something called a patcher. So we overwrite the code generated with an illegal instruction. That's the UD2A instruction on the right upper side of the slide. And when executing these instructions on the POSIX operating system, an illegal instruction signal will be sent to the process. CACAO catches this and says, oh, probably a patcher is about to be executed, and looks up in a table if on this position there's a patcher. And when there is one, the class gets loaded, linked in the memory, compiler stubs get generated, things like that. Afterwards, the memory is overwritten with the original contents of the instruction, and the address of the method to be executed is inserted. And execution is then continued at the point where the illegal instruction occurred. So it's completely transparent to the program that class loading took place and things like that. Okay, now to the important question. We've seen such a JIT compiler does many nasty things, but what can a JIT compiler do for hackers? Let's try to look at it from this point of view. The input to a JIT compiler is complex data. It's Turing complex data, so it's rather complex data. The just-in-time compiler takes this input, makes a transformation, and outputs Turing complete data again. So that's a rather difficult transformation. And the best thing is, the result of the transformation will be executed. So probably we can have some fun here. Additionally, some just-in-time compilers are on highly exposed places. Let's think of a Java applet. It's loaded in the Java interpreter in your browser. ActionScript and JavaScript are executed by a just-in-time compiler called Tamarin. It will be in the upcoming Mozilla releases. Microsoft Silverlight's technology, Flash applets. There are cheats everywhere, and we can give them our data. And there will be more cheats in the future. But there's a big problem for hackers when they want to exploit such stuff, because just-in-time compiler fork have really huge test cases. You call them programs, we call them test case. So we have such insane big test cases like Eclipse, Tomcat, or JBoss, which do many nasty stuff, and the just-in-time compiler is really almost bug-free when it runs Eclipse. So this is a really big test case. But nonetheless, there are attack vectors. We have tried to group them in 3 levels of seriousity, and the highest level were undefined behavior in language specification. For Java, there's no undefined behavior as far as we know, but just think of C or C++, double free, it's undefined behavior, can be exploited. So undefined behavior is always bad stuff, but in Java we don't know about undefined behavior. When transforming the Java language into bytecode, a transformation takes place. Question is, are there any problems when transformating stuff? And are there any quirks when mapping the constructs of the language to the bytecode, which is a much simpler language than the Java language? And of course, we can try to attack the generated assembler instructions. Are they always generated correctly, or are there some tilts? This were the stuff we were looking at, and yeah, we then did a 2-hour code review and found quite a few things. But it has to be said, a few things. First of all, CACAO is a research VM, so it was never designed to be secure. We execute programs on our development machines. Yes, so it was not a criterion, but it has to be said that each vulnerability we found is actually just a bug. It's the same thing like in many software, it's just a programming error which will be turned against the programmer by a skilled hacker. Okay, I will now present the stuff we found and the source code, what it looked like. But before I come to this part, I want to make the point clear what's an integer overflow, because we found a lot of integer overflows, and therefore you should know what it is. There's a 16-bit value and 12 bits are read, but let's ignore them for now. Think of it as a counter. On the left side there's the binary representation, then we have the hex representation, and then a decimal representation. And the thing is, when you always increase the counter by 1, it starts to tick. And somewhere, and it's in line 4, we have a leading 0 and a lot of 1s. This is interpreted as 7FFF hex. And this is the biggest integer which can be represented by a 16-bit value. And when we increase the counter 1 more, an overflow occurs. It's just a normal binary addition, but the interpretation of the result changes, because the most significant bit is a signed bit. And when it is 1, the number is negative. And so the next value is minus, and it's the smallest value representable by a 16-bit integer. And this is where the overflow occurs. And yes, when we increase the count again, another overflow occurs on the last 2 lines from -1 to 0, but in this case the 1 just drops out on the left side when adding it, and we are back at 0. A very interesting effect also occurs when this 16-bit value is tried to be stuffed into a 12-bit value. And this is what happens quite often. In line 4, you see the biggest representable integer in a 16-bit value. It's 7FFF. But when truncated by 4 bits, this number suddenly becomes negative. So if one component of the software uses 16-bit and there's a test, is the value larger than 0? And the answer is yes. And you put this value into a smaller register or in a smaller bit field, it suddenly can become negative and you can access memory perhaps somewhere else. This is why integer overflows are evil. Okay. Here we found something on PowerPC 64. We found a 32-bit integer overflow when accessing data segments. Data segments are created to store constant data, and it's a 64-bit address machine, so the data segment could possibly be 64-bit wide. And the problem is, in the marked lines, the displacement is cast to a short, which is just a 32-bit value. So instead of accessing memory at a positive offset, it could be accessed at a negative offset because we cut off a few bits. Nonetheless, this bug is not exploitable because there are no data segments this large. Java class files always have limited size. They have a limited numbers of constants, limited numbers of methods, and 4 gigabit is just too big. It does not fit. But we found more. On AMD 64, we found another 32-bit integer overflow. This time, the argument of a conditional branch, which gets generated by the function emit GCC. And in the last line, you see the argument or the branching offset, it's just a 32-bit value. But it is, again, a 64-bit machine, so here a truncation happens and we again have an integer overflow. But that again, it is not exploitable because no method is larger than 2 gigabyte of instructions because in class file they are much smaller already. On PowerPC 64, we then found a 25-bit integer overflow, and this is very close to be exploitable, but just not. Very bad. Again, it's conditional branching, and on PowerPC 64, there are 32-bit fixed-size instructions. And when branching with a condition, a lot of bits get used just for this is a branch, this is the condition, these are the arguments, and there are some bits left for how far to jump. And when generating the conditional instruction, the displacement gets truncated, but again, it's always inside the range of a method, and so it cannot be exploited. But on PowerPC 32, we had luck. We found a 16-bit integer overflow, and this is about a virtual table of an object. In the virtual table, my friend Peter will explain this in more detail. There are all the method indexes, and we can overflow it. And we will overflow it, be negative, come back again, and so trick the bytecode verifier into executing stuff. It thinks it is secure. We implement a very nice feature with that bug. And we also found a bug on what we call medium level serosity. This is a bug with exception handling in Java. When you think of Java exception handling, you always think of the try catch block, and you cannot enter the catch block without an exception. That's not possible. It's only entered when the exception occurs. And you catch this exception, and you have this exception object, E. It's a variable for this block, and it's always there. And you can only enter this block with an exception. That is true in Java, but it is not true in Java bytecode. And this is what gets executed, finally. In Java bytecode, you can have something like a fall through in the C switch statement, where you can fall through the labels as well. And you can do that in Java bytecode. And whoever wrote the exception handling code in CACAO was not aware of this or did not think of this nasty detail when initially writing the code, because he thought of Java, but he should have thought of Java bytecode. But no one is really that familiar with that, and so this seems to have happened. And by chance it happens that CACAO, this exception object, which is the argument for the catch block, by chance is an integer register. And by some good arithmetics, we can control the contents of that integer register, then fall through and have fun again. Okay, and now Peter will show you the exploits, and yeah, thanks.
So to actually implement exploits for these vulnerabilities that we have found, we're going to implement fake Java objects from within Java code, populate their methods with arbitrary code that will be our shell code, and then pass control to the shell code by executing one of those methods. So let's have first a look at how objects are represented in CACAO. Any reference type, any Java reference type like object or string is just a plain pointer to an object that is located on the heap, and such an object consists always of an object header followed by all instance fields. If you now call a method in Java like toString, the code that will be invoked is not determined at compile time but rather at runtime. And the selection of the codes works as follows. If you have the object pointer and invoke, say, object toString, first the virtual function table pointer is loaded from offset 0 of the object pointer. Then the name of the method is converted to a method index, and this index is used to load the entry point of the method from this virtual function table. And finally, this, the executable code is called. Java arrays are Java objects too, so they contain an object header. Then this object header is followed by the number of elements in the array. This is collectively called an array header, and the array header is followed by the array elements. We want now to construct such a data structure from within Java code, and we can use arrays to construct such a thing. We can use a byte array to put some executable machine code into the byte array. We can use an array of integers of the native word size to create such a virtual function table, and we can use such an integer array to create this object header. But we still need to set up the pointers correctly in the data structure, so we need two things. One, given if we have a Java array, we need to retrieve the address of the first element of this array to set up those pointers. And to pass control to our code, we need to convert some arbitrary address to a Java reference type, like say object. To solve both these tasks, in our first exploit, we're going to use the 16-bit integer overflow that Roland has presented. And this overflow happens under some circumstances where the entry point is loaded from the virtual function table. The offsets into this virtual function table are in fact 18-bit wide. But in some situations, the offset is just truncated to 16 bits. So let's have a look at what happens with this offset after truncation. So let's now suppose that the offset is not truncated to 16 bits, but just to 4 bits. So we have here such a table. In the left column, there is just a sequence of increasing offsets. And in the next column, we truncate this offset to a 4-bit signed value. So we see that for some offsets, they will keep the same value. Then for some other offsets, they will become negative. And then for the next set of offsets, they will become positive, but have some different value that was intended. And these offsets are then used as indices into this V table. So if we want to address the first group of methods, they will be addressed correctly. Then if we want to address another set of methods, the index will become negative, and instead of loading the entry point of the method, some garbage pointer from before the virtual function table will be loaded. And for the next group of methods, the entry point of some different method will be loaded instead of the real entry point. At this point, we have a misbehavior where if we call a method, some different code will be executed, and we can use this misbehavior to implement interesting stuff. We write such a big class, it's called big, and it contains some 16,000 trivial methods that all just take an integer argument and return this argument as return value. And we add two more methods, one int to object and one object to int, that both take some argument and just return some dummy value. If we now call this int to object, because of this integer overflow things, one of those 16,000 methods will be called instead, and because of the calling conventions where addresses and integers are passed and returned in the same registers, the argument will be just reinterpreted into some different type and just returned. So using such a class, we have implemented an interesting feature, an unsaved C-style cast for Java, and the type system and type safety is bypassed at this point. So having these two cool casting functions, we can go on and construct our fake objects. So we create an instance of this big class, we create our shellcode that can be arbitrary machine code in a byte array. We create this virtual function table with enough entries for enough methods as an integer array. Then we use our object to int function to get the address of this byte array to populate the virtual function table slots, but we need to always add a fixed size constant, which is the offset of element 0, because we have this array header thing before element 0. Using again object to end, we set up this object header in a integer array. At this point, our fake object is complete, and we use now this int to object thing to convert the address of the fake object header into a Java reference type, a object. And finally, by invoking some virtual method on this reference type, we pass control to our shellcode. I'm going to demonstrate this now. Okay, so we have implemented this and compiled already. I'm not going to compile it again because the compilation of this huge class just takes too much time. Let's see what CACAO we have installed here. Okay, it's It's 0.97. It's, I think, some previous release, but it's just the default Debian package installed on the system. So I'm going to invoke the thing, and we just have an operating system shell. This may not look like an interesting thing because you can just fork off a shell from within Java code, but the idea is that if you use this in this sandbox environment like browsers or cell phones, then you actually bypass the security policy of the virtual machine. So let's go on. So for the next exploit, we're going to use different techniques to retrieve addresses of Java objects and then to convert arbitrary addresses into reference types. We're going to use the exception handling mechanism, as Roland already told. So I'm going to briefly describe how exception handling works in CACAO, what code will be generated if you create such a try block and a catch block. So suppose you have a try block, and in this try block you throw an exception, then this exception object is put into a special integer register, namely scratch register 1, and a special function implemented in assembly language is invoked. This function then lookups correct exception handler block depending on the dynamic type of the exception object, and passes control to this appropriate catch block. And the catch block accepts this exception object to be located in scratch register 1, and it reinterprets the contents of this register as a Java reference type. So this implementation is perfectly legal for compiler-generated bytecode, because, as Roland already said, within Java you can reach a catch block only through the exception handling mechanism, but by writing handcrafted bytecode, you can actually bypass this exception handling mechanism. Now, to retrieve the address of a Java object, we're going to use a much trivial and easier technique. Namely, you can use the default implementation of object to string, which already prints something like class as at address in memory, or you can use the default hashcode implementation, which sometimes also can return the address of the object in memory. So using one of them, we implement such a address of function that returns the address of the object. And in such a static initializer, we again set up such a fake object header with a fake virtual function table and with shellcode, as we did in the previous example. So at that point, we already have this fake object available. Now the only task left is to convert the address of this fake object into a reference type. So we're going to write some Java bytecode assembly function. This is written in a language that's called Yasmin. It's just a bytecode assembler. We write a function and create a try block and a catch block. In this try block, we load this address of the fake object on the operand stack. Then we create enough local copies of this address. So we have now some 12 copies on the operand stack, and then we save all those copies into Java locals. Java locals in CACAO are preferably allocated into registers. On PowerPC, there are 10 registers reserved to allocate locals into them, but the last 2 copies will be put into memory. This is important because in the next step, we're going to perform an integer addition on these 2 in-memory copies of the address, and this will force the compiler to produce machine code that will load these locals from memory into scratch registers, namely scratch register 1 and scratch register 2. After the integer additions, our object pointer is already in this crash register 1. We discard the result of the addition. So we could now go on into the catch block, but to keep the bytecode verifier happy, because we're going at the end invoke a virtual method, and because here the operand stack is empty, we need to push some object on the operand stack for this invoke virtual to work. So we simply push null. It's not important, and it doesn't discard the contents of crash register 1. And now, without throwing an exception, we directly fall through into the catch block. At this point, this constant null will be just replaced by the contents of crash register 1. We invoke a virtual method on this exception object, and at this point, the shell code gets executed. So I'm going to demonstrate this too. We have actually implemented this code for several architectures, and this exploit is very portable because because it doesn't rely on the backend, but rather some problem at a higher level, at the design of this exception handling mechanism. So it will probably work on most architectures that CACAO supports. So we have such dynamic architecture recognition. Then we invoke, depending on the architecture, the correct version of this handcrafted bytecode. And this needs to be tuned for every architecture, because there are small differences like number of registers and how to actually get some content into the integer crash registers. So we have several implementations, and finally have this exploit 32 class with machine code in those byte arrays for every architecture one, and then again some dynamic architecture recognition, selection of the right shellcode, and that's it. Okay. You should now be able to build this because it's rather small piece of code, and we'll execute it. CACAO call. Okay, and we again have our shell. I'm going to shortly run this example in the default Debian Java interpreter. I think that's the GNU Java interpreter. And what we will see, the code dies with a null pointer exception. This means the right thing has happened, because in this handcrafted bytecode we have pushed at some place the null constant. This null constant is interpreted as exception object, and the whole thing fails. So, thanks for your attention.
Okay, I hope you had fun watching the exploits working. We just wanted to demonstrate techniques how to exploit virtual machines, and it works perfectly, because most of the time you can use the machine to get addresses of objects in memory and stuff like that, and in the right moment you kick in and take over control. We think it's possible in every virtual machine, because every virtual machine will have such bugs. We just used CACAO for this demonstration because we were very familiar with the code. And we tried to read hotspot code, but it was quite difficult to just read the code, so we didn't find anything there. Okay, if you still trust CACAO, you could join and port it to your operating system. It's rather easy to port it to a different operating system. It's perhaps a 3-week task. So if you have fun, it's GPL code, interesting signal handling, memory overwriting, code batching. You learn a lot about your hardware architecture. Yeah, okay, thanks for your attention. Yes, of course.
Hello, I've got a question, maybe idea. As there are getting interpreters of one languages in another languages are becoming popular. For example, PyPy tries to interpret Python into .NET and then interpret .NET, or Silverlight takes .NET and into JavaScript and so on. Does it mean that it widens possibilities of attack vectors because now we have 2 interpreters and 2 dynamic languages?
I think that one interpreter is written in another language, so you won't be able to exploit here, but you can always attack the bottom VM. So your exploit has to work through all the layers of interpreters and finally attack the last one, which is running on silicon. But I think that's possible, yes?
Any more questions? I don't see any more questions, then thank you for your presentation.